Hi, everyone. My name is Nadolina Brajuka. I'm a bioinformatician at the Vertebrate Genome Lab at Rockefeller University. We are a sequencing and assembly hub for the Vertebrate Genomes Project. Today, I will be presenting an automated decontamination pipeline and an example of a vertebrate reference genome that's been curated with the rapid curation pipeline from the Wellcome Sanger Trust Institute. So the goal of the VGP is to assemble and make publicly available high-quality reference genomes for all 70,000 vertebrate species. We've broken this number down into 4 phases, which you can see here, and are currently at the tail end of phase 1, where we are trying to assemble a high-quality genome to represent each of 260 orders. This is an overview of the workflow the VGP is currently using. So of course, we start with extracting our DNA and producing a set of raw reads. These reads then go into our assembly pipeline. We're currently using version 2.1, and we generate a draft assembly of the genome. And then that draft goes into decontamination and curation. And these last 2 steps here are going to be the focus of my presentation today. I'm going to start by talking about decontamination. The goal of decontamination is just to remove any scaffolds that are from contaminant species or are from the mitochondria, because we assemble the mitochondria separately. So VGP assemblies were originally decontaminated using this process that had a mixture of manual and automated programs. But as the VGP tries to scale up and assemble all 70,000 genomes, we wanted to make this process fully automated. And so we started working on this pipeline. So once we get a draft assembly out of the assembly pipeline, it goes into this first step, which is a repeat masking step. And then this repeat masked assembly goes into 2 sub-processes. So the first sub-process is trying to identify all the non-target contaminants using Kraken-2. And then in the second step, we are blasting the draft assembly against a database of mitochondrial sequences that was curated by NCBI. And those results are filtered by this script here, which only retains scaffolds that are very, very confidently mitochondrial in origin. So at the end of this, we get a compiled list of contaminants and mitochondria by scaffold name. And GFA Stats uses this list to remove those scaffolds as well as any terminal gaps, and generates a new assembly in FASTA format that can then go on to curation. So to validate this automated pipeline, we used 19 VGP assemblies that had already been decontaminated with the established process I mentioned earlier. And so 3 of these assemblies had no contaminants or mitochondria. I used them to check for spurious results, so those are not here. We have 16 assemblies that are reflected in this figure. And so on the left, what we're looking at is the percent of scaffolds that were either true positive, false negative, or false positive, where 100% is not the full genome, it's just the sum of true positive, false negative, and false positive. And so what these dark gray bars show is all the true positive scaffolds that were identified. And so you can see that it works really well, even though there are some incongruencies among some of these bird genomes that we have down here. So I was encouraged by these incongruencies to look at, okay, how much is actually being removed from the genome when I use my pipeline? And so what we found is very little. Not that removing them is not important. We want to make sure that there's no contaminants, but of course, if there are issues, then very little is actually being removed. But what we see here is a percent of the bases in the entire genome that are either true positive, false negative, or false positive. So 100% is the size of the genome, and that is shown sort of by these light gray bars, even though the scale only extends to 0.2%. And so what we can see is that very little of the genome is actually made up of these contaminant scaffolds or mitochondrial scaffolds. So after we've decontaminated our assembly, it goes on to curation, which is where we manually modify the genome in an attempt to improve its contiguity. And so right now, we are mainly doing that with the rapid curation pipeline developed by the Wellcome Sanger Trust Institute. And this pipeline is mainly based around the use of pretext view, which is a program that allows you to manually modify a high-C contact map. So this is an example where I curated the heterohyrax brucei, the rock hyrax. And so these are two high-C contact maps shown in pretext view. And so what we're looking for is this contiguity along the diagonal here, but we're seeing this noise at the right and along the bottom. And so what pretext view actually allows you to do is pick up these pieces and join them into the scaffolds that they're interacting with here in an effort to make highly contiguous scaffolds and chromosome level scaffolds. And so you can make breaks, joins, or inversions in this pretext view program. And so this is what the final curated HBrucey looks like. And of course, at the very end of this, we get a FASTA file that has the updated assembly. Assembly statistics also reflect an improvement in the curated assembly. We use this scaffold AUN metric, area under the curve, which is just a little bit more robust than an N or NG50. And we can see that that improves in the curated assembly. We can also see that the number of scaffolds decreases significantly in the curated assembly, and that reflects that we've just made a significant number of joins and have much larger scaffolds and chromosome level scaffolds. Assembly statistics are great, but it can be hard to conceptualize what's actually going on in a genome pre and post curation. So what I've done is I've gathered the lengths of all the scaffolds pre-curation and post-curation. If you look at the left-hand end of the graph here, you can see that there is an overlap in pre-curation and post-curation scaffolds at this lower length end. And what this means is that there are very small scaffolds that are not being assembled, but they're also not being resolved by curation. They're likely highly repetitive and just can't be resolved. But of course, the most important observation is this peak of scaffold lengths around the mid-length that disappears post-curation. And what's happening is these are just being assembled into these larger chromosome level scaffolds down here. So again, we have much fewer scaffolds after curation, but they are larger and more highly contiguous. To conclude, decontamination and curation are critical steps in generating quality reference genomes and will continue to be necessary as the VGP continues towards its goal. Automated decontamination is very effective and will be necessary as we try to increase our rate of assembly. And then the Wellcome Sanger Trust Institute's rapid curation pipeline streamlines the curation process and makes curation accessible. Thank you to my lab, in particular, like my bioinformatics team, as well as the Wellcome Sanger Trust Institute for helping me with decontamination and curation. Please check out our GitHub, Twitter, and our link tree for more information. And thank you for listening to my presentation.